Well, welcome back, everybody. It looks like about half of you came back. Okay. Now, I hope that everybody had a chance to get on the Canvas course and explore and find out where all the things are at, where your assignments are at, and so forth. Any questions about that? Any questions about Canvas and where to find what? You know, your textbook, your quizzes, general information. Yeah. Any questions about that? Nope. Okay, that's good. All right. Well, let us continue. And we were on wrong one. Canvas changed their program a little bit, which I'm not crazy about. Okay, let's stop for a second. Got some people in here. All right. So we ended up here. Now, what we're talking about matter and the changes that matter undergo. Now, there's only two types of changes. One is a physical change, okay? Now, a physical change basically means that it's going from one state being a solid, liquid, or gas to one either going from a solid to a liquid or to a gas. But chemically, structurally, that's the important part. Nothing happens to that chemical. A classic example is water. We all know we have solid water, which is ice. Okay, it is still chemically, structurally, has a formula H2O. Okay, as we heat the ice up, it undergoes a change and goes into the liquid state. Chemically, it's still H2O. And if we continue to heat it, it eventually will go to the gas phase and becomes a gas or a vapor, but it's still chemically H2O, okay? Physical change, it is just this change of a state, has nothing, nothing happens to it chemically. Okay, now a good example would be as the follows. Let me show you here. And so if we have H2O, normally we can draw, here's H2O, two hydrogens bonded to oxygen. We generally draw an arrow to demonstrate that something's going to happen to it, be it chemical or physical, but something's going to happen to it. And in this case, it remains H2O. So if we got a solid, we put in parentheses S for solid, and we heat it up, that solid, which is ice, now becomes liquid, okay? And it's still H2O. Nothing has been done to it chemically. The only thing that happened to it, its physical state has changed now to a liquid. But what can also happen is we can take H2O, we can hit it with some electricity, give it a lot of energy, and we can literally break it up to form two new species. We can take the H2O, hit it with electricity, we do undergo what we call electrolysis, and break it up into hydrogen gas and oxygen gas. Notice that we have totally changed the formula. So in the first step is a physical change versus a chemical change, okay? And that's the main difference between the two. In that physical change, we do nothing structurally to the way the molecule is put together, whereas chemical change, we totally change the structure and everything completely, all right? So right now we are just simply talking about physical changes. And some of these you're familiar with already, okay? For example, a solid going to a liquid, we call that melting, okay? Nothing high tech about that, right? We're all familiar with melting, the term melting. When the liquid goes to a gas, we call that evaporation, or vaporization, or boiling, okay? And when a gas goes to a liquid, guess what? Condensation, right? You have a cold drink on you, ice cold water, right? You let that glass sit there for a while. What happens to the outside of the container? It gets wet, right? That is called condensation, because the water vapor that's out in the atmosphere hits the surface of that cold container. Energy is removed, okay? And it causes the molecules to get closer together and they condense. Okay, so the outside of the container gets wet. It's called condensation. Okay, nothing magical about it. All right, it's a matter of putting energy into the system and taking, either you put it in or you take it out. Energy, transfer of energy. When the liquid goes to a solid, obviously we call that freezing. So you put your ice cubes in the freezer. They're in the liquid stage. Temperature drops, you remove energy from the system. The molecules now are coming closer together, okay? And they solidify, we call that freezing, okay? Now, it is feasible to go directly, now up to this point, we've been going through all the three phases. We go solid into the liquid, into the gas, okay? Or vice versa, gas into the liquid, then to solid, back and forth, but it's going through a state. It is feasible to bypass a state. And technically, it really is not bypassing it. It is going through, but it happens so quickly you don't even see it. Meaning that we got this solid that goes directly right into a gas, okay? We call that sublimation. And you might be familiar with this. You've seen it. You've probably seen dry ice or worked with dry ice or played with it, or done something with it. Dry ice is nothing more than carbon dioxide that's in a solid phase that goes directly from the solid into the gas phase, okay? And we call that sublimation. So in essence, it doesn't stick around with the liquid phase very much. It just goes directly to solid to gas. Now, the opposite of that is taking that same gas. We can take carbon dioxide and we put it in this instrument that we can solidify the carbon dioxide. We call that deposition. So we can get some CO2 gas running through this little instrument here that will convert it back to a solid, okay? We call that deposition. Now, all these different names that we have, it's a matter of energy. It's a matter of putting energy into the system or breaking energy or taking energy away. And it's a matter of interfering with the interaction of what I tend to use is these magnets here. See a bunch of little magnets here. All right, and so what's happening here, there's a connection between the molecule. This could be a molecule of water interacting with another molecule of water. And when we put energy into the system here, this could be the nice and ordered state. All the magnets are nice and solid, ordered. It represents the solid phase. I put energy into the system and I break up that interaction a little bit that these magnets have with each other. Now, they're still somewhat ordered, but not as ordered as a solid phase, but they become a liquid. And if I continue to add energy, all I'm doing is breaking up that interaction between the molecules and I break it apart, okay? And they go into the gas phase. And it's a matter of just the exchange of energy, okay? Either putting energy into the system or taking it out, okay? When it comes to the physical changes, okay? To go from the different physical states, solid, liquid, and gas. Okay, and their respective names are given as follows. Now, demonstrate that in an equation, a chemical equation, we write it as follows. So here I used the example earlier of water, which is right here, H2O, okay, interacting or having having energy put into the system. Here we call boiling, because you take a pot of water, right? Put a pot of water in the stove, you put energy into the system, eventually the molecules start moving around, that water starts boiling, they separate from each other, you break up the interaction that the water molecules have with each other, and you shove that water into the gas phase, okay? And we denote that by this equation, chemical equation, where in general terms, I'm going to introduce you to general equations. We have an arrow, which most of the time is a one-way arrow. We can have a double arrow, which represents it's reversible. But in general terms, we can say A, whatever A may be, undergoes some process, which could be a physical process or a chemical process, and we don't denote that by this arrow to give us something B, okay? So in general terms, there's a chemical reaction or a chemical process. A with the arrow, okay? The A represents the reactants, okay? To the left of the arrow are reactants. Those are the species that something's gonna happen to it, either chemically or physical. And then B over here represents the products. All right, and so B represents something that is the result of whatever happened to this process, either a physical process or a chemical process, okay? So we write these chemical reactions, and that's what we got here. Now, in this particular case, you may not know the formula for water or for any chemical, but you can notice, you analyze it, it's H2O to begin with, okay? And guess what? It is H2O after the arrow. So structurally, it is still the same, okay? Now, I could write any formula up here, and you may not know what it is, and that's okay, but I hope that you can analyze the formula and say, hey, structurally, it looks the same. Nothing happened to it. I still have H2O in the beginning. I have H2O at the end. The only difference is the state denoted by those arrows and by the letters in parentheses, okay? Where S represents a solid, S in parentheses, L represents a liquid, and G represents a gas. And so structurally, H2O, nothing happened to it. The physical state changed because in parentheses, we went from a liquid to a gas. And so we call that boiling, okay? So this isn't a, hold on, I'm getting a unstable, my internet, my Cox has been acting up this morning, so hopefully won't lose connection here. All right. Okay, so we get a physical change. All right, so now this example is a boiling, okay? There we go. And the diagram shows us the whole process. In this process, the physical changes is a matter of putting energy into the system or taking it out. Okay, that's all we're doing here. You can see the diagram of a solid where, the spheres represent whatever chemical we're working with. So they're all nice and ordered here. And then we put energy into the system. So we put plus energy, okay? Plus energy, and we break up the interaction between the molecules. And we cause these molecules to be less ordered and less structured and take it out from the solid phase into the liquid phase. So you can see now the spheres are still there, but not as ordered and structured as they were when they were solid, okay? We continue to put energy into the system, okay? And now we're breaking that interaction between the molecules with respect to other molecules. These, what we call intermolecular forces, we're breaking them apart, resulting in these molecules to be separated from each other and sending everything into the gas phase, okay? And so it went from solid, liquid to gas. Now, once you're in the gas phase, we can take energy away from it. And sure enough, you can take a gas, reduce the temperature, you're taking energy away from it and go from gas back to liquid. Okay, we call that condensation or condensing. And if you continue to remove the energy, take the energy away from it, bring it down maybe to, let's say, 0 degrees if this was water, we then send it back to the solid phase, okay? It's all a matter of energy. Some solids, like I said, carbon dioxide can go from a solid directly into liquid, call that sublimation. And if we take energy away from it, we go and have deposition, take that carbon dioxide gas and convert it back to solid, okay? But the whole thing is a matter of energy back and forth, and it's reversible. This physical process of going from one physical state to the other is reversible. It doesn't change the structure chemically. And if this was water, H2O, and all of the different phases here will still remain H2O. Not a chemical change, but a physical change. Okay. All right, so atoms are always moving. Okay. They're always moving, even in a solid state. We might tend to think that as they sit there in a solid state right here in the far left, that they're quiet, but they're actually vibrating, constantly vibrating. And now I'm just going to, excuse me, in the liquid phase, they're going to vibrate a lot more and compared to the gas, because as far as energy state, who's a higher in energy, the gas phase is very high in energy with respect compared to the liquid and the solid stage. But everything, atoms are always moving, even in a solid state. So when you heat ice, the water molecules can gain what are called kinetic energy, okay? That's movement energy. And so when they pick up energy, you cause these molecules to move even faster, and they start separating and from each other, from the solid phase to the liquid phase to the gas phase. It's a matter, again, of, of energy and taking energy in, putting energy into the system, or taking it out, okay? And this is what this is all about, okay? Going from a different one phase to the other. It's a matter of putting kinetic energy or movement energy, or removing it if we're going to go the opposite direction, okay? Excuse me. Now, when we have chemical changes, the molecules literally break apart and form and rearrange themselves to form other molecules of something, okay? We have what we call a chemical reaction, okay? The starting material is totally destroyed and a new material is created. When you burn gasoline, for example, you have what we call hydrocarbons, and we ignite them, and we totally change the structure of these hydrocarbons and now create, let's say, carbon dioxide and water. It's one of the main products of combustion of hydrocarbons. For example, we have a general formula here. Make sure you get the right one. If you notice here, we have C subscript X, H subscript X. That's a general formula. And the thing to notice, let me draw a little bit bigger. CX, HX. X can be integers, okay? It could be numbers. Right now, it's a general formula where if you notice that you had nothing but carbon and hydrogen, okay? C is for carbon, H is for hydrogen. We're going to talk a lot more about the different atoms here combined. And we call that a hydrocarbon, okay? A hydrocarbon. Now, in the presence of oxygen, when you burn that fuel or gasoline, you need oxygen, right? You got fuel injectors, or you got an old carburetor vehicle, you got to have oxygen into the system, and then you ignite it. Spark plugs, for example, will give you an ignition, and that hydrocarbon explodes, and bam, by that explosion occurs, it shoves a cylinder down and allows you to move, your vehicle to move, okay? Eventually you burn that hydrocarbon, okay? The two products you get is carbon dioxide, denoted by CO subscript 2, and water, okay? And so that's a one-way trip, okay? Because we can't take, at this point in time, that carbon dioxide and water and reverse it and convert back to hydrocarbon. That'd be cool. We can do that. Okay. And so we completely change the chemical of the hydrocarbon. We completely change the structure of the oxygen to create two new products. So that is a chemical change. Okay. A chemical change. All right. All right. So what kind of things indicate that there's a chemical change? Well, rust. You know, I used to have an old pickup. There's a lot of chemical change in my old truck. Hit a lot of rust. Okay, so rust is a good indication of a chemical change. That iron in the metal has undergone oxidation. Okay, or anything that burns, obviously. Any burning of paper, any burning of fuel, anything that undergoes combustion is a chemical change occurred. Okay. Occasionally, you may see release of bubbles. You might if you're doing a lab, you put two reactants together, and there's not a lot of heat being given off, but there's bubbling going on, and that's a good indication that a chemical change has occurred. A good example would be Alka-Seltzer. If you take Alka-Seltzer, dump it in the water, you get boiling going on. Well, if you look at the ingredients, you got a little bit in Alka-Seltzer, you got a little bit of citric acid and a bicarb. So the bicarb and the citric acid in solution, they react with each other, forming a little bubbling action going on, and that's a chemical process, okay? Chemical change. You might get two liquid solutions who are clear. They may be colored or not colored, but they're clear. And the moment you mix them together, you get a solid, a precipitate, a formation of a solid. We call that a precipitation. That's a good indication that a reaction process, a chemical process occurred. So you get precipitation. Or, excuse me, you might put two reactants together and it gets hot to the touch. Again, a good indication of a chemical process, or light could be given off. You get those sticks, those little fluorescent sticks, you take them and you break them and light is produced, okay? That's a good indication that a chemical process, fire bugs, lightning bugs, that give off the light at night. There's a chemical process occurring there, okay? And it could be a change in color. You might get two clear solutions, you end up with a blue solution or any other type of color. Or an odor could be given off, okay? And that odor could be very nice smelling, or it could be bad, okay? A good example of some good smelling products are things like wintergreen. Some of the mints that we ingest, they're made up of what we call an acid and a base, two chemicals, an alcohol and an acid that by themselves smell not too good. You mix them together, you form a general formula of what we call an ester, and you get things like the smell of wintergreen, the smell of banana oils. Okay, they smell pretty good. All right. So let's take an example of a chemical change. Notice here we have in words, we have chemical reaction between sodium metal and chlorine gas. With time, we're going to learn how to decipher that statement and convert that into into a chemical reaction. Okay. So this is just the beginnings of, but eventually we're going to be learning how to interpret what we're given in words and put it into a chemical reaction. Okay, so what it says here that sodium metal, okay, which we would look up the formula for sodium and A, okay, And they're telling us that it is a solid, but we're going to know that based on its position on the periodic table. If you notice the periodic table behind me here, okay, you're going to be able to determine whether that element is a solid, liquid, or gas. Okay, we're going to learn that of all the elements there, only 2 elements are liquids. About a dozen of them are gases, and the remaining of the elements are solids. Okay, and so we're going to know that sodium is a solid, so hence we have in parentheses S. Chlorine gas is what we call diatomic. What that means, look at the term, listen to the term diatomic. D-A-atomic, diatomic. Di meaning 2, atomic meaning atoms. There are 7 elements that are what we call diatomic, okay? That by themselves, they don't exist very well. They're not very stable. They have to exist with another element of itself. Hence, you have a subscript, Cl2, okay? And we'll have more to say about that. And we're going to know that chlorine is a gas, hence G, okay? Now, when you take sodium metal, and you can go on the internet and search the reaction of, you'll see a lot of crazy reactions that people have done. Is they take sodium metal and they dump it into a lake, and it's pretty aggressive reaction. Sodium metal is so aggressive when it reacts with water. It gives off a lot of heat and a lot of energy and a lot of hydrogen gas, and it explodes. But if you take sodium metal, okay, and you react it in the presence of chlorine gas, which is a poison. In fact, if you live near a municipality that treats water treatment place, some places use chlorine gas to treat the water, get rid of bacteria. If you ever see a cloud of yellowish, greenish gas coming at you, get out of the way, because they got a chlorine gas leak. Because this chlorine gas by itself would just destroy the inside of your lungs. And so it's a poisonous gas, a very reactive metal, sodium. They react together, and guess what? They make something you can put on your French fries. Okay, sodium chloride, aka table salt. Okay, and this is the fascinating part for me, is when I first saw this crazy reaction 100 years ago when I was starting to learn chemistry. The only difference that happened here is that their sodium lost a tiny electron, and chlorine picked up that electron. There was a transfer of an electron. And it's like if I were to just take one hair, when I compare the size of sodium, when I look at this, we're more on this, but it's analogous to taking a hair and plucking it off me, and I become something else completely, 100%, totally different. One little electron, the power of electron, which is the same type. These electrons, they have static cling. The same electrons that are running through your electronic equipment to run this computer. And that exchange of one tiny electron just totally changed the chemical properties of a new product. It just mind boggles me, the power of electrons, and they're so tiny. So anyway, here's an example of a chemical change. Totally, it's not reversible. The arrows are one-way arrow, okay? And can we make it go back into sodium and chlorine? Yes, but we got to put energy into this, a lot of energy into the system. This reaction occurs spontaneously on its own to make it go back from table salt back to sodium metal, and chlorine take a little more extra energy to get it back there. Okay. Excuse me. All right. So, good example of a chemical process. All right. So, now, granted, we've not, it's early in the ball game, so to speak. We haven't talked about the formulas and what they are, but that's okay. You can take a look at what you're given and break it down, do an analysis on the reactants and the products. Okay. Now, what you're going to learn is this. Let's take the first one. You notice it says it's written N, nitrogen, and then 3 ammonias, okay? And written with a subscript telling us what this tells you is this. 99% of the time, the first element that you see written is what we call the central atom, okay? And then what follows the central atom are all the other atoms that are bonded to the central atom. We're going to learn that here we have nitrogen and then 3 hydrogens bonded to the central atom. We're going to learn that if, let me change the color here. We have nitrogen and we have 3 hydrogens bonded to the central atom, okay? Now, obviously, we can't draw it all the time, so we write it in this manner with nitrogen followed by 3 hydrogens. So those 3, whatever follows the central atom, and you'll be told who the central atom is, okay? These hydrogens are bonded to the central atom. Okay, so this is the formula for ammonia. You're familiar with ammonia. If you had to use any ammonia window cleaner, that is the formula. Nitrogen with 3 hydrogens bonded around it. And so we see NH3, okay? We see the arrow, and then we look at the product side again, we got NH3 again. So that tells you, hopefully, that, nothing happened chemically, because I still have NH3 in the beginning and NH3 at the end on the right side of the arrow. So I go back and I look at my physical state. Well, it went from a gas to a liquid, okay? So what happened here must be a physical change here, okay? It's got to be a physical change because chemically nothing happened to the formula of NH3. Unlike the next example, that again, you start off with NH3, but when you look at to the right of the arrow, a good indication that you had a chemical process is you have the plus symbol, okay? The plus symbol should tell you, something happened here. Notice in the first example, there was no plus symbol. I still got ammonia and ammonia before and after. But here, I've totally broke up the nitrogen and the hydrogen. In fact, what's happened here, I broke down the NH3 and I created, what's created here is N2, which is nitrogen gas, and H2, which is hydrogen gas, okay? So the fact that there's a plus there should tell you, I got 2 new products. I got 2 new products, guess what? I made it's a chemical process, okay? And sure enough, this is an example of a chemical process because I made 2 new products. 2 new products from my starting material, which was in this case one species, NH3, that's it. Now you might start noticing numbers in front, coefficients. Like let's take a look at that hydrogen. Okay, hydrogen is diatomic. Remember, I mentioned the term diatomic. There's only 7 elements that they exist. They have to be paired up with each other. 7 of them. We're going to learn which ones they are. Hydrogen is one of them. Nitrogen is another one. Notice there's a subscript too. Okay. Chlorine, we just did chlorine. That's one of them. So there's 3. There's 4 more we're going to talk about. But notice the number 3 in front of it, in front of NH3. This is called a coefficient. Okay. Compared to the subscript. Okay, the subscript is constant. Okay, always will stay as a 2 or whatever number it may be, okay? The coefficient can vary. That tells me with a 3 in front of H2 that I need 3, there are 3 molecules of hydrogen. So hydrogen is, I can draw a bond between 2 hydrogen atoms. Okay, just like I did right there, okay? Now, instead of having to draw 3 of these species every time, I simply put a 3 in front of H2. These are the same thing, okay? But this is the shorthand way of writing 3 separate molecules of hydrogen. So that 3 tells me how many of those hydrogens. I can change that number 3 any number of times. If I need 6, 7, 8, 10, 1,000, a million, I can change that all I want. The subscript is etched in stone. And we're going to learn how to make that subscript. But once we know what that subscript is, it's etched in stone, we leave it alone. The coefficient, we can change whatever number we need, okay? And notice there's 3 of them. So that means that there are a total of 6 hydrogens on my product site. And there are 6 hydrogens on my reactant site, okay? Because we're going to learn too, based on the conservation of matter and conservation of energy, we have to balance our chemical reactions. If I start off with 10 atoms of whatever on as a reactant, I need to have 10 atoms of whatever as a product, okay? That is due to the law of conservation of matter. And notice they put numbers in front because these equations had to be balanced to make sure that the conservation matter has not been lost. Okay, so notice we got two nitrogens on the reactant side. Guess what? 2 nitrogens on the product side. Now they may change differently. They might be a little bit different with respect to where they are chemically, but it's still hydrogen. Okay, hydrogen in the form of ammonia, or hydrogen in the form of gas, or hydrogen in the form of anything. It's still hydrogen. Okay. All right, let's take a look at the third one. On first analysis, you might think, oh, that looks like H2O, water. But it's not, because notice there's a subscript O, okay? So we got H2O2, and we look at the product side to the right of the arrow, and guess what? We see another plus symbol. That right there should tell you, chemical reaction. Sure enough, it broke down, H2O2 broke down to form hydrogen gas, and here's another diatomic, oxygen. Oxygen is also diatomic. This, by the way, H2O2, you might be familiar with it. If you ever dyed your hair with hydrogen peroxide, that's the formula. Or you cut your finger, that's what you use to put on your finger to get rid of the bugs, hydrogen peroxide. So this, the fact that you got a plus symbol and you totally created 2 new products should tell you that we have a chemical reaction here, okay? All right, number 4, we got H2O2 again. All right, we look at the product side, H2O2, same thing, formula-wise. So that should indicate, okay, no chemical reaction occurring here. It's got to be a physical process. And that is verified by the physical state of it went from a liquid to a solid. And all they did was just drop the temperature and solidified it, okay? And so this is an example of a physical change, okay? And finally, the last one, we got C6H6. Notice something. Remember the one where I said earlier about hydrocarbon, where you have a mixture of nothing but a carbon and hydrogen? Okay, we got a hydrocarbon here. nothing but carbon and hydrogen put together. There's 6 carbons, 6 hydrogens. And we look at the arrow, and on the product side, again, nothing there, but nothing happened to it. It's still C6H6, same hydrocarbon. And we can verify again by looking at the physical state. It went from a liquid to a gas. Okay, so this is an example of a physical change. Okay. So the takeaway from these reactions, yes, you're not familiar with what they are structurally so far right now. That's okay. But you can look at the products that you have and the reactants and just analyze how they're put together. And from that information, be able to discern whether it's a physical change or a chemical change. Again, is a good kind of rule of thumb. If you have a plus symbol on the product side, more than likely a chemical change has occurred. Okay, as in the case of number 2 and number 3. Okay, any questions about that? Yeah. Okay. Let's talk about an element versus a compound and versus mixture. Okay. So an element is just one type of atom only. Okay. It could be a single atom, for example, He, which is helium, or it could be what we call diatomic. Okay, like oxygen. Oxygen, at least here on Earth, along with the other diatomic, and there's only 7 of them. We're going to list them here in a bit. These are elements that by themselves are not stable. Okay, and so what happens is they hook up with another element of itself. So oxygen is an example. Hydrogen is another example. By themselves here on Earth, they're not very stable. So they have to hook up with another, bond with another element of itself. Hence, we call it diatomic. Okay. And elements cannot be broken down any further. They're broken down as anything. If we break an element down, we start breaking them into their subatomic particles. Okay, into the protons and the neutrons and the electrons. And so elements, that's as far as we can go. Okay. Now there's 118 elements. And no, we're not going to have you memorize all 118 elements. No, not at all. But you should be familiar with at least the first 20. Okay, with respect to the symbol and with respect to their name. And then as we proceed through the semester, we'll be adding more to that list, okay? All right. Now, compounds, when you get 2 or more different elements, different atoms, and they bond them together, you form a compound, okay? And so we did earlier, we had a diatomic example was hydrogen gas, H2. Or it could have been helium, He. Okay, these are elements. That's it. But let's say we put together 2 different elements like hydrogen and oxygen. Okay, we created a compound. Okay, H2O. 2 different elements make up what we call a compound. Okay. All right. And then, of course, something is pure, pretty self-explanatory. It's basically something is pure, it's just that particular particle, whatever it is, all by itself. I mean, pretty self-explanatory with respect to something that is pure. Compared to a mixture, it could be made up of 2 more different particles mixed together, okay? And the thing about a mixture, you can separate the 2. Okay, whereas something that's pure, that's, you already know, you can't separate it because it's already by itself pure. Okay, and so we have a flow chart to kind of help you out, and you see a lot of these diagrams. We tend to use a lot of these diagrams to depict these compounds. For example, down at the bottom, let's take a look at, matter. All right, so matter could be either broken down into a mixture or a pure substance. All right, so if we go to the right over here, notice how in this diagram here, we have a mixture, two more different moieties, whatever they may be. They could be different elements. They could be different diatomic elements, okay? But here, we got two of them that are put together, okay? Those are diatomic. They represent, here's two spheres together. That represents a diatomic molecule of some sort. And then we got the spheres where they're all by themselves, okay, in black color. And so here we got a mixture of a diatomic element and some type of other element. Two different species here. On the right, we got a magenta color and the red and the black. So it looks like we got a mixture of three different elements, okay? Three different elements. A pure substance, if we go to the other direction, okay, we could have a pure compound. Now, the thing about a compound is whenever two or more at the minimum, different compounds, different elements are put together to form a compound. Here's H2O. You got the yellow spheres that could represent hydrogen, and then the red, which could represent oxygen, okay? So that's a compound, H2O, and it's pure because it's all you see there, nothing but, it looks like Mickey Mouse ears on there, right? And then on the right side, you got sodium chloride. You got the two different colors of spheres that represents two different compounds combined, two different elements, I should say, or atoms that represent a compound, okay? Elements, on the left side here, okay, it could be pure atoms. In this case, Ne is neon, okay? And then we have diatomic, they're two spheres again. It's all, both examples are pure because there's nothing else in there. So we can have either pure atoms or pure molecules of some diatomic molecule, like oxygen or hydrogen, or nitrogen, and we'll learn about those there's seven diatomics that are diatomic atoms, okay? So this is a breakdown of pure atoms and a mixture. You'll see a lot of diagrams. We utilize, like I said, a lot of diagrams, okay? All right, mixtures. There's a lot of examples of mixtures out there. Metal alloys. Okay, for example, gold, the gold jewelry that we utilize, it's not pure gold. Pure gold is very soft, and it's by itself doesn't lend itself well to make jewelry. Okay, so normally what you have is a mixture of gold and what are called alloys. Okay, like 18 karat gold or 24 karat gold or whatever carat you're using. It's a mixture of that gold plus some other element, and the mixture gives it strength so you can utilize it. Brass is a mixture of copper and zinc, okay? Stainless steel is a mixture of carbon and iron, pure iron by itself. We couldn't do anything with it, it's so soft. It doesn't lend itself to function well to make buildings with. So they're mixed in with other things, okay? Granite, tap water, why is tap water a mixture? Well, if you analyze tap water, you'll find a mixture. You'll see all types of salts inside the water, calcium, potassium, sodium, chlorides, and so forth. So it's a mixture of a bunch of stuff. The air around us is a mixture, okay? Something that's pure would be like table salt, nice, clean, separated sodium chloride. A diamond by itself, diamond by itself is made up of nothing but carbon. And you think about it, this is the power of these atoms relative to each other, and how the structure put together can have a big effect on the property of your whatever you have. For example, diamonds are made up of nothing but carbon. Okay, carbon. Imagine this. Carbon. There's another type of carbon where graphite has nothing but carbon. That graphite is a dry lubricant. It's very soft, and it's used as a dry lubricant. It's made up of carbon. And here on one hand, you have carbon as a lubricant, and the other hand, you have carbon as a diamond, which is the hardest thing on earth. Okay, they're made up of carbon, both of them. And you might ask, well, why is that? Why is it that one is a dry lubricant and the other is the hardest thing on earth? What is it about that makes diamonds so hard? Well, it's how they are put together relative to each other that changes the properties. And diamonds are put together in such a manner that they're extremely tough, okay, and extremely hard, the hardest thing on earth, okay? But you could change it a little bit and you make something that's a dry lubricant. Polystyrene, we're all familiar with polystyrene. It's a foam, very soft. You can take it, crush it in your hand, no problem. But I can take polystyrene, change its structure a little bit, and I can make material that is tough enough to use it as lumber to make things with, okay? And it's all made up of nothing, both cases made up of carbon and hydrogen. So structure has a lot to do with the properties of your chemical. And what this is the electrons surrounding the molecule. So we go back to electrons again. That's such a big factor. All right, so distilled water, why is distilled water pure? Well, as I heat it up and I drive it away from the bulk of the container, and I collect on the still on the other end, I collect pure water, okay? And mercury is a pure substance, okay? So diagrams, a lot of diagrams. Here on the first diagram that depicts an element, specifically a diatomic element, okay? Because the two balls here are, the two spheres are connected to each other. They're the same color, the same size, okay? In the middle, that represents a compound where you have two or more different elements combined. It looks like the clear one is the central atom, okay? The way it's drawn. We got the central atom here, the white one right here, and whatever this gray part could be is bonded to the central atom, okay? And again, this is a pure example of a pure compound because it's nothing else other than the two gray bonded to the two clear. Same with the first one, pure. Okay. Where the third one is a mixture of two elements. Here's one element here, the gray. And then here's the second element, looks like, and then we have a compound of some sort. So we get a mixture of two elements and two different compounds. Okay. So if we look at these diagrams, again, we're just gonna look at them, break it down, and determine what they represent. So A would represent an element, specifically a diatomic element, right? Okay, and it's also pure. There's nothing else in there. B represents a compound, because a compound is a combination of two or more different elements bonded to each other, okay? And so you can see here we have the dark center one with three clear, white ones around it, okay? So some type of a compound. C is a mixture of elements, two different elements. D represents, again, an element. And nothing else but a dark sphere. That's it. E does represent a compound, okay, a pure compound, nothing else but the dark and the clear sphere bonded to each other. F is another mixture, specifically of a diatomic element and a mixture of two compounds. Okay, do we know what they are? No, we don't. We're just going off the color and the shape of the material. Okay. G, we have again a mixture of a compound and an element, and then H is simply an element. And I could even, based on the diagram, I could even further state that more likely H is a solid. Okay, and I can say that because it's very structured and very ordered. Okay, very structured, very ordered. Compared to the others are all kind of loose. They could be gases, could be liquids, but definitely not solid compared to H. Okay. All right. Now, let's talk about the elements themselves. Hopefully you've downloaded the periodic table, okay? The one that we utilize. Now, each element has its unique name, its unique symbol, and it has its own number, okay? Its own number. So we have the periodic table here. Now, the one we have here is not updated, but if you look at the table, yeah, all the elements have been discovered now, up to 118. They're working on them right now to find some more, but the table we have for you, specifically number 115, number 117, number 118, it's down here in the bottom right. They have generic symbols. They have been given official names now. They were discovered, I believe, 2015, when the rest of the table was filled up. Okay, so each one has their own unique symbol. Some of them have one letter, some have two letters. Okay, but the ones with two letters, note, the first letter is capitalized and the second letter is lowercase. Okay, for example, BE, which is beryllium, capital B, lowercase e. Others have single. K for potassium, okay, one letter, all right, Li for lithium, so on. So I would be familiar with the first 20 at least. This is calcium, Ca. And then we're going to, as we proceed, we're going to add others that we're going to utilize. We're not going to have you memorize all 118. No, not at all. Okay. But we will utilize the periodic table quite a bit. Okay. All right. So each element has a unique name, symbol, and number. Okay. First letter is always capitalized. For example, H for hydrogen, C for carbon. And if it has a second letter, it is lowercase. Quite important, okay? Quite important, because if you inadvertently write the second letter capitalized, you have named a totally different species, okay? For example, C lowercase o is a symbol for cobalt. If the second letter you write it uppercase, you are designating as carbon monoxide. Totally different. Okay, so be careful when writing the second letter. Make sure it is written properly, because you may be wanting to write carbon. Let me show you what I'm talking about here. Here's cobalt, lowercase o. If that oxide O is written uppercase, you are writing carbon monoxide, which is definitely not cobalt. And you know, when we talk about in science, we got to be exact. Okay, we're talking about, you know, be exact with what you're trying to write and state. Okay. All right, let's clear this up. Now, a lot of them do have English names. For example, H for hydrogen, O for oxygen, He for helium. But there are some that have Latin names. So Pb, which is lead, comes from the word plumbum, which is Latin, meaning Latin, waterworks. Au comes from the Latin term orium, which means golden dawn. So the symbol for gold is Au. Okay. Now, be familiar with the first 20, and along with the following ones: Ag for silver, okay, Au for gold, Pb for lead, Br for bromine, okay, I for iodine, and Hg for mercury. Okay. Now, we're going to introduce something I want you to be aware of. Notice we said bromine here, okay, as compared to bromide, IDE. Notice there's a difference, INE versus IDE. Notice there's a difference between chlorine versus the name chloride. Okay, chlorine, you don't want to breathe, it's a poisonous gas. Chloride, no problem, you put that in your French fries. Okay, totally different species here. Okay, we're going to learn about that. Okay, chlorine, chloride, bromine, bromide. Okay. Totally different. So we're going to be careful in how we state what are we dealing with. The INE, the ein is the element. The IDE is not the element. Okay, more on that later on. Now, we're going to, the physical states of these elements, okay? When we talk about the physical states, we have to define the temperature that we're working with. And we're working with at 25 degrees Celsius, which is basically room temperature. Obviously, the physical states will change depending on the temperature. All these elements, if we were on the surface of the moon, would not be, definitely not be solids, right? Okay, so we have to define the physical state. So when we talk about the physical state, we're talking about 25 degrees, which is basically about room temperature. And we are 1 atmosphere pressure. We are right now 1 atmosphere pressure right now, okay? Now, of the 118 elements that we have, only 2 of them are liquids, specifically mercury and bromine, okay? All right, now, I'm going to have to pull up the periodic table here in a second. But notice here we got hydrogen, nitrogen, oxygen, fluorine, and chlorine. Okay, 1, 2, 3, 4, 5 listed here. Okay. And then we have, I'm going to show you where the noble gases are on the periodic table. And so we have 7, so let me pull up the periodic table. On the far right, the very far right here, notice there's a group Roman numeral 8A. Okay. Up on top has a Roman numeral 8. 1, 2, 3, 4, 5, 6, 7. There's 7 elements here. Those are called the noble gases. Okay. They're called noble gases because they're very unreactive. And I want you to remember this number here. This Roman numeral. Oop, where'd it go? Okay, the Roman numeral 8. This is the magical number 8. The driving force of these elements is to obtain 8 electrons around its outermost shell. Okay, 8, the magic. This will make more sense here when we start talking, but I want you to remember the magical 8. Okay, 8 electrons. There's something about that number that nature says, I need 8 electrons around my outermost shell. We're going to learn that these electrons occupy shell energy levels, and the driving force to become stable is to have 8 electrons around it. And to become stable, either one or two things are going to happen. It's either going to lose electrons or gain electrons to get that magical 8, okay? But more on that down the road here. So we have 1, 2, 3, 4, 5, 6, 7 noble gases, okay? These are 7 noble gases plus 7, 8, 9, 10, 11, 12. Plus these 12. So we have 12 elements that are gases, and everybody else is a solid. Okay, so here's a periodic table, color coded for you. Everybody in yellow is a gas. Okay, and then mercury and bromine right here are the 2 liquids. And everybody in blue is a solid. Okay, so once you got those guys kind of set, automatically you can say anybody, you can pick any element given to you, even though, let's say iron's right there. I ask you, well, what's the physical state of iron? Well, it's a solid. Okay. What's the physical state of potassium? Right there, find potassium, it's a solid. What's the physical state of oxygen? It's a gas. Okay. All right. What about bromine? Bromine, oh, guess what? It's a liquid. Mercury, okay, it's a liquid. So this table there, at a glance, if you mark up the periodic table with this information, you know automatically who the physical state, what the physical state is. Okay, at a glance. Right. Oh, okay. Remember those diatomic elements I was mentioning to you? Remember I said there's 7 of them? Well, here they are. Hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. Something to help you out, have no fear of ice cold beer or beverage. H is for hydrogen, N in no is for nitrogen, F in fear is for fluorine, O is for oxygen, I is for iodine, C is for chlorine, not carbon, chlorine, and B is for bromine, okay? So 118 elements, 7 of them are diatomic, meaning that at our conditions here on Earth, they cannot exist by themselves. They have to partner up with another element of itself, okay? And they're still an element. If they combine with a different compound, then they're different element, they're compounds. But right now, they're elements, okay? Okay, so 12 gases. Gases, 2 liquids, okay? The remainder is solids, okay? 7 of them are diatomic, okay? And the reason we state this because eventually you're going to be given words to describe a chemical reaction like the one we just did with sodium and chlorine. and you're going to have to be able to state their physical state, okay? But just following that, knowing that periodic table there, and knowing these 7 diatomic molecules, you're good to go. All right. So now, of these, almost done here. This is also important to know. Okay. Of these 118 elements, they're broken down into 3 types. Type number 1, a metal. Type number 2, a non-metal. And type number 3, a semi-metal. Okay. And it's crucial to know which one is which, because it's going to tell us what type of bond they create when we start getting into the structure of these. So we got 3 types only: metal, non-metal, and semi-metal. Okay. And if you look at the periodic table that we give you, there is a little stair step that helps you out to determine that. See that stair step on the periodic table? To the left of the periodic table, okay, are the metals. To the right of that stair step are the non-metals. Okay, so that stair step helps you out to determine who's a metal and a non-metal. And so the ones in kind of a pink color here, including hydrogen, notice the hydrogen's in the far left column. And also notice that there's Roman numerals on top of the column. Those Roman numerals are very helpful to help to determine some things here. So they tell us something here, okay? We'll get to that. So hydrogen's in the far left, but that is a non-metal, okay? Everything in pink is a non-metal. Everything in blue is a metal. And then the yellow green color is a semi-metal. What that means is they have properties of a metal and properties of a non-metal. They're like a mule. Okay, I don't know if you know this, but a mule is a combination of a horse and a donkey. Okay, horse and a donkey get together, they make a mule. A mule has properties of a donkey and properties of a horse. And that's what semi-metals have. They have properties of a metal and properties of a non-metal. Now put this in long-term memory. Metals want to lose electrons, okay? They always want to lose electrons. And non-metals, guess what? They want to gain electrons. And the number of electrons they lose or gain depends on what group they're in. We'll get that here in a minute. But the thing is, remember I said the driving force is to get that magical 8 number? So by losing electrons, they get to that magic 8 number, 8 electrons around its shell. By gaining electrons, they tend to get to that magical 8. Okay, but we'll get to that with time, but just remember that metals lose electrons, non-metals gain electrons. Okay, all right, let me see. All right, so a couple more slides and we'll be done with this chapter. Metals, some of the properties of them, they're shiny material. Metals tend to be, you can smash them, spread them out. All metals tend to be solids except mercury. Mercury is the only liquid metal, okay? Their density, remember that ratio, mass over volume? They tend to be unusually high, okay? They have a very high melting point. It takes very high temperature to get those metals to melt, okay? They're very good conductors of heat and electricity, metals are, okay? Compared to non-metals, they generally have a dull appearance, okay? If they're solids, there are not all metals, non-metals are solid, but the ones they are tend to be brittle, okay? And a lot of the non-metals are gases. Their density tends to be low, that ratio of mass over volume. Okay. They tend to melt at a low temperature, and they're very poor conductors, which makes them excellent insulators. Okay. Other than that, look at the periodic table. Okay, be able to determine the name, at least for the first 20 of the ones we gave you. Okay, determine on slide 34 tells you, okay, of all the elements there, which ones are solids, which ones are liquids, which ones are gases. Okay, just by their position in the periodic table. Okay, looking at that little stair step, that helps you out to determine who's a metal, who's a non-metal, and which one's a semi-metal. Okay, or you may hear the term metalloid. It's another term you may hear. Okay, and then determine which ones are diatomic. Have no fear of ice cold beverage. Okay, all of that information we're going to eventually use. This is information we're going to use when we start putting reactions together, put chemical processes together, and be able to learn how to balance equations. Okay, very crucial. All right, that is the end of chapter 1, ladies and gentlemen. You know what I forgot? Let's stop recording.